So that is the most important thing. And also we are devoting the time through the interdisciplinary board called minor in the quantum technology. So different departments are there which are involving inside this course, so that now a new era it is coming up, boom it is coming up like a quantum technology. So sir can give many guidance, suggestions inside this direction as well. So as a department it is concerned, we are working on different two things we can say, as a materials as well as the theoretical. So materials we are dealing with the energy as well as different materials for the different applications. And as well as we are also working on quantum technology, condensed matter physics, DFT studies. So theoretical aspect it is there, that is also is covered inside this one. So as a department, as a DS, we have applied for DST fees grant, sir. So we got about 2.19 crore, and under this one we have procured X-ray diffractometer, which is necessary equipment for material scientists, and also we have having Raman spectrophotometer as a for the materials it is required. And just this last year we have applied DST fees grant about 10 crore to have FESEM units as well as HPC, so that HPC, that is high programming, computing programming it is there, which is helpful for the theoretical physicists as to do certain quantum technology things inside this direction. So not only this one, our PhD students, they are working abroad. Some of them, they got top 2% scientist position. MSc student, they are taking PhDs in VNIT as well. They are also having taking degrees from IITs, IISERs, also from abroad institutions. So they are securing very good positions as well. So I wish to thanks that again to Deshmukh sir, that he has allowed us to make this event successful. So we can listen him, and we will not waste much time inside the introductory part. Thank you very much.
Thank you, sir, for your inspiring words and for highlighting the achievements and vision of our department. To share insight about IIT Indian Association of Physics Teachers, I now invite Professor Anwane sir to address the gathering.
Thank you, sir. Respected Professor Sankpal, our today's speaker, Sir P.C. Deshmukh. I recognize presence of many physics teachers here, Professor Kamal Singh, Sapre sir, Prabodh Chandra Deshmukh sir, Apte sir, faculty members of this college, faculty members of various institutions in Nagpur who are associated with physics. On behalf of IIPT, that is Indian Association of Physics Teachers, I am here to tell you certain basic things about this organization. This IIPT was formulated in 1982, 42 years ago, by Professor D.P. Khandelwal. And this institute, this association has grown to the extent that it is the biggest scientific subject association in the country. We have 20,000 members. Professor Pranam Chandra Deshmukh is Vice President of IIPT, and I would like to appeal the young budding students to become a member of IIPT and get connected with IIPT so that you can know various activities going up for propagation of physics, for cultivating scientific temperament in the society, and you will be able to connect with the proper resource persons. With this, I continue my say. Thank you very much.
Thank you, sir, for enlightening us about IIPT and its initiatives. Quantum technologies are shaping the future of science and engineering education. To brief us about the quantum technology minor course and UG lab, I now invite Professor Ganesh Patil from VLSI department to brief us about the various initiatives that VNIT is taking.
Good afternoon, everyone. together work to develop the minor course. So my student friends, actually our motivation is, the government of India has started the national quantum mission, and I will suggest the students to opt for this minor course also. So we started this course, almost Professor Ram Karthik knows it, almost 7 to 10 students opt for this minor course. And we hope that from the month of July, when the course will start, you all would opt for this course as well. About the development of the UG lab, actually our plan was to develop the quantum technologies laboratories in our institute. So being a program initiator, actually the team of the bio faculty has started the initiative. So Professor Ram Karthik, Professor Uday, Professor Akhil, and Professor Mansi Radke. So we started the interdisciplinary activity, and we sent a proposal to the government of India. Actually, you remember the day on 15th September, at the time of convocation, our DST Secretary Karandikar sir came and told us that we have to develop the UG lab in our countries. So we took the initiatives and we sent the proposal. Fortunately, now it has been gone through the review process as well. And the cap amount of 1 crore the government of India DST told us. So we wrote the proposal, and soon we are going to develop this lab in our institute as well. So my friends, so this is a good initiatives we have started taking in our institute. I hope the students will get help of it. And we are fortunate that the Professor PC Deshmukh is here and he will guide us regarding the quantum technologies as well. Thank you very much.
Thank you, sir, for sharing valuable information about this exciting academic initiative. Now I invite Professor Sunil Bhatt from Electrical Engineering Department to give a brief introduction of our distinguished speaker, Professor PC Deshmukh. Please.
Dear all, it's a very difficult word that task has been given to me, because he said I will introduce in brief, which is very difficult, but I will try. So as I was talking to sir, after finishing his MSc and PhD from Nagpur University, he moved to Europe for postdoc and later on to US, where they stayed for many years. And but then they decided that they will not stay at US and they will come back. And I'm talking this in 1970s, where everybody was eager to move to US and not work in India. So at such moments, both the couple took that decision to move to India and one work here. So he joined IIT-Madras, and for a long time he taught there as a professor. And basically he is a theoretical atomic physicist and a hardcore teacher, because he has taught at so many organizations like IIT. Currently also he is teaching at IIT Tirupati, IISER Tirupati. Then he is associated as arbitrary professor at School of Computer Science and Engineering, RV University, Bengaluru. And he has also been associated with IIT Mandi, Georgia State University, University of Western Ontario, London. So everywhere he is associated with so many institutes and so many students. And that is how he recognized Ram sir also as one of them who had interacted with him, and was very happy to see him here. And his research group is one of the leading contributors to the relativistic many-body studies of attosecond dynamics in atomic photonization process. Also, he has made significant contributions to the applications of Lambert W and Polylogarithm functions to the problems in pure and applied physics. Dr. Deshmukh has authored 2 books, Foundations of Classical Mechanics and Quantum Mechanics, Formulation, Methodologies and Applications. And as we were discussing, he had told that the 3rd book is in pipeline, which is specifically developed for this quantum technology course under National Quantum Mission. And he has also done lectures from NPTEL. So all those who are taking quantum technology minor here, they will be very happy because little material is available on this, and such a good teacher teaching those things in NPTEL will really benefit our students. So he has been recently appointed as the ANRF Prime Minister Professor at Central University, Kerala, Kasargod, where he will soon join. So we are very much thankful that he has accepted our invitation and speak to such an interesting but complicated topic. That is why I guess he has chosen the right word, Enigmas to technologies. Thank you very much.
Thank you, sir, for that insightful introduction. We now come to the most awaited program of most awaited moment of the program. Before I proceed, I would like to add one thing, sir, that I was immensely benefited by the MSc program at IIT Madras, especially your course on atomic and molecular physics. So thank you for that, sir. It is my proud privilege to invite Professor P.C. Deshmukh to deliver his talk on quantum physics, Enigmas to Technologies. Sir, we are eagerly waiting for your enlightening address. Sir, the stage is yours.
Can we go full screen?
GST नहीं होता क्या?
साढ़े चार भी नहीं बजे, साढ़े छह कैसे बजाएंगे?
मैं 2 मिनट तैयार बनी सुना
2 घंटे बहुत
नींद भी आ रही है तो नींद नहीं आती हाँ बेचारा
इथे येऊन खूपच आनंद होत आहे. Very many thanks to Professor Armane, to the Indian Association of Teachers, which has organized this series of 3 lectures. Professor Shankapal for inviting me for the first lecture here at VNIT, which is particularly an interesting coincidence because when I went to Professor Shankapal's office, the head of the department's office, there is a list of names of the previous heads of department. The third name is that of Dr. Edki, who taught me wave mechanics when I was a student in the postgraduate department at Nagpur University. So I had my first course from your head of the department here. It's a great privilege to be here. Many of my very close friends are here. Very rich moment for me coming back to Nagpur because this is where I had my entire education from the first standard in the primary school, middle school. I went to Hadas High School. Prior to that, I was at Saraswati Vidyalaya, and then later studied at the Science College. Now it is called Institute of Science, but I was a student when it was called as Science College. Then the Nagpur University Postgraduate Department of Physics. And many who are over here, I have worked with them, fought with them, learned from them, and most importantly, had some of my best time in my life with them. I think the most interesting story I can tell you is how I got selected for admission to the MSc program in the postgraduate department. But I think I will keep it for a personal, private interaction rather than speak about it in public. But that is perhaps more interesting than anything else I might say today. It was a difficult period for me because I was not very successful as an undergraduate student up till BSc. I was a fairly good student in my high school. But between high school an MSc when I was doing my BSc at the College of Science. And perhaps if there are undergraduate students over here, they might find it interesting. I never wanted to get into academics. I never wanted to get into physics, mathematics, or anything of this kind. I wanted to join the Indian Air Force. And my next choice would have been to join the army. I never thought that I was cut out for civilian life. And I'm afraid I have struggled with that all my life. I was even selected in the first round for recruitment for the Indian Air Force. I have not told anybody at home. My brother is here. Prof, he's more than 10 years older than me, so he knows everything. And when I was called for an interview for the second round, everybody got to know about it because the letter came home and I could not intercept the letter before it reached my parents. And then my mother and 3 of my sisters, they emotionally blackmailed me. It was awful. When I was talking to them, I thought that my plane had crashed and they were looking at my dead body. And I thought I was seeing it with my own eyes. And I have very often not listened to elders in my family, but somehow this emotional blackmailing was too much of a pressure and I succumbed to it. It had consequences because I revolted and I did not want to study. So I was spending most of my time as an undergraduate student with friends. We had a music band and I was not interested in formal university education. So I had very turbulent years at that time. Till it came to the point that I realized that ये ऐसा करके नहीं होने वाला, कुछ पढ़ाई करनी पड़ेगी. And during those turbulent years, Prof Dada used to take me to one mathematics professor in Ramdaspet, who taught me some very interesting things in mathematics. So I was not good at taking the exams. I think Professor Deshmukh or somebody. I forget the name. But he used to take me to his house, drop me there, and then come back and pick me up. And that is when I got interested in symbolic logic, ended up writing an article for our college magazine on George Boole's work. And then, this was the time when I was finishing my BSc. And I think the postgraduate department was operating out of the law college premises at the time. So every night he used to take me to that law college in his office. And for several months, I put in some effort to get back into mathematics and physics. And I really enjoyed being a physicist. I often think that perhaps I might have enjoyed life more as an Air Force officer. But the next best thing perhaps certainly is to be a physicist. It's wonderful. So do we have the full screen here? Let me get back to the main topic. We had it earlier, we seem to have lost it. So it is in a state of superposition, being there and not being there, perhaps. Can we have the full screen?
1 minute.
So all these institutions I have been associated with are like medals a soldier would sport on his coat, and that is the closest thing I have come to belonging to the armed forces. So enigmas to technologies. And we have these two stalwarts here on the screen, Albert Einstein and Niels Bohr. So I'm sure everybody has seen this picture. It's arguably, I think everybody recognizes as the photograph which has got the largest intellectual density in one screen. I don't like this picture. It is very incomplete. It doesn't have some who should be there. Here they are. And the contributions of Satyendranath Bose, C.V. Raman, and Meghnad Saha are not known sufficiently. I would like to begin by pointing out that in many ways Meghnad Saha's work in the 1919, and this is before the formal papers by Schrödinger and Heisenberg in 1924, 25, 26. Saha's work was in 1919, outstanding work. The fundamental difference between classical particles and quantum particles is that classical particles are distinguishable and quantum particles are indistinguishable. The first person to recognize this was Satyendranath Bose. And I think his name ought to be at the very top at the foundations of quantum mechanics. But I will probably talk about it on Monday when I'm giving a talk on contributions of Bharatiya physicists. But to me, it is a very important thing because when Planck made the hypothesis to explain the blackbody radiation, he just did curve fitting. Nothing more than what a high school student does. You know, you give a curve and then ask him to determine some coefficients and some polynomial function. And Planck went on to say that it was an act of desperation. He did not think there was any physics in it. And indeed, there was absolutely no physics in it. But it worked. And Planck argued against his hypothesis for the next 8 years. So he proposed this hypothesis in 1999 December, toward the turn of the century. But he accepted this only after Einstein accounted for the photoelectric effect in 1905, where E equal to h nu got its meaning. In fact, Thomas Kuhn points out that the origins of quantum mechanics should be attributed to Einstein in 1905 and not to Planck in 2000 or 1899. But the story doesn't end there, because E equal to h nu involves quantization of the electromagnetic field, which was done by Satyendranath Bose in 1922. So we have proposed that H should be redesignated as PeV constant, the Planck-Einstein-Bose constant. This is a very serious proposal. We have a paper on that, which is written along with Professor Ahluwalia, who is the president of the Indian Association of Physics Teachers and the director of the National Physics Laboratory. Dr. Achanta Venugopal is also a co-author on this along with one of my students, Aniket Bhargav. This paper is not published as yet, but it will come out very soon. So this is a very strong recommendation. As a matter of fact, in my book on quantum mechanics, I do refer to it as PeV constant, and in many of the other papers that I've written after that. So this much about the origins of quantum mechanics, but what are the enigmas associated? Life is full of decision making. Do I do this or that? Do I go left or right? Is the switch on or off? Is it 0 or 1? Very often the question after marriage changes. Instead of will you marry me, it changes to why did I marry? But it's either 0 or 1, and it is left or right. So if you pour sand, you expect 2 heaps under it. If there are 2 slits, you expect 2 heaps. But what you see is several heaps and alternate fringes. These are the bright and dark fringes. And as Feynman says in his lecture, which many of you would have seen on the YouTube, the basic ideas of quantum physics are contained in the Young's double slit experiment. Now, this is really very shocking, but it can be very easily understood from this picture that if you drop 2 pebbles in a pond, the spherical waves will superpose, and depending on whether their maxima and minima are in phase or out of phase, you will get either brightness or 0 intensity. So this is like the wave picture, and this is at the heart of wave-particle duality. So you can interpret it as wave-particle duality. But I would like to emphasize that quantum physics is much deeper than wave mechanics. Wave mechanics offers interpretation of many phenomena in nature, but not every. There are features which go beyond wave mechanics. And quantum physics is a deeper theory. Wave mechanics is one of its representation. Matrix mechanics is another representation. There are many different formulations of quantum mechanics, like wave mechanics and matrix mechanics are 2. Feynman's path integral approach to quantum mechanics is a third very famous one. There are other formulations based on scattering theory developed by Wigner and so on. There are, in fact, there is a paper in the American Journal of Physics which I will be happy to share a reference to, which sums up something like 9 different formulations of quantum mechanics. And each formulation accounts for the properties of nature to a fair extent. In most part, they are equivalent, but not fully. And there are features which wave mechanics accounts for, but there also are features which it doesn't. So here we are talking about superposition of probability amplitudes, which really accounts for this interference pattern. So let's push this Young's double slit experiment further. So you've got an electron gun and you shoot particles, you shoot electrons, you know it is a fundamental particle. And even if you shoot it at a speed which is very low, so that at one time there is only one particle in the apparatus at a time, even then, with passage of time, a fringe pattern develops instead of the 2 heaps that we would expect. So this is very spooky. So you are of course interested in knowing the truth. How can the electron go from both the particles? It just cannot. Okay, because it is a fundamental particle, you cannot split it, you cannot slice it. So you decide to spy on the apparatus. What you do is you shine light on the 2 slits. Because if you shine light on the 2 slits, so this is called as a which-way experiment. And in the which-way experiment, you shine light and then see the scattered light. If it comes from the upper ray, you know that it has come from the left slit. If it comes from the lower ray, you know it has come from the right slit. But see what happened. Look at this picture. Before you did the which way experiment, you had these fringes. Now you do a which way experiment and notice that the fringes are gone. Spookier. Began spooky, now it becomes spookier. Let's do something further. Let's take a lens and bring these two rays to a focus. The lens has the capacity to bring the two rays to a common focus. And if you do that, you would lose information about whether it came from the upper ray or the lower ray. You will lose information about the left slit or the right slit. This is a which way eraser. Whatever information you got from the which way experiment is now erased and the fringes come back. It gets spookier and spookier. Right? Okay, now let's move this lens. This lens is here. Move it over here and follow the red spot of the laser pointer and move the lens somewhere down there. Okay, it has gone to the ground floor now, and perhaps crosses the Earth, goes beyond our solar system into another galaxy. But the lens is there, and it can bring those two parallel rays to a focus. It has that capacity. And just the fact that it has that capacity is sufficient to serve as a quantum eraser. Now, this is why quantum physics is so enigmatic. Because you would ask, how does an electron which is coming from the gun toward the two slits know whether or not there is a lens in the apparatus somewhere? And how does it care that the lens is somewhere else? These are mind-boggling questions. And they need the minds of intellectual giants like Niels Bohr, Albert Einstein, Schrödinger, Heisenberg, Satyendranath Bose, John Bell, and so on. And I'll come to some of their works. So, here, look at the remark I have at the bottom. Krupaya apne vani par dhyan de. It is a very serious appeal. Because you sometimes read it in books, sometimes you listen to this in some lectures, including YouTube talks and so on. Say that the particle is here and also there. No, it is not here and also there. It is not at two places at the same time. If you try to find where it is, the interference is destroyed. The particle is not there. What is there at the two places? The probability amplitude. Okay, the probability amplitude is at both places. It's not the same thing as saying that the particle is at both places. So one has to be very careful. You must use very precise language and cannot say that the electron is both at S1 and S2. It is a superposition of probability amplitudes which are non-zero at both the slits. So you are getting into mathematics. So this is the which way eraser which I mentioned. Even if you put it very far away, this experiment is called as delayed choice eraser. And this was a thought experiment which was suggested by John Wheeler. But equivalent experiments have actually been carried out, and everything that I am saying here has been experimentally verified. You can ask, how does the electron know what auxiliary experiment will be performed after it enters the apparatus? Will there be a lens? Will there be a which-way experiment? Will there be? No, the electron doesn't know. The electron is very stupid. It doesn't have consciousness. So that is not the right question to ask. And that is not the right language to use. The question is not about how does the electron know what the apparatus is. Again, I will like to appeal, कृपया अपने वाणी पर ध्यान दें. The electron doesn't know anything. So that is not the vocabulary which is appropriate for this. We know what the apparatus is. We are carrying out experiments. And we are interpreting these experiments according to a certain theory. And this classical physics theory does not account for it. Quantum theory accounts for it very easily. Let me come to that. These are some very interesting references. Some of you can ask for these references. I'll be happy to share with them. But I share these references. There are very interesting experiments which have been carried out, not just with electron guns, but even with large particles, with fullerenes, for example, with nanoparticles which have got something like 7,000 sodium particles. This was published just about a month ago in Nature. Beautiful experiments. The moral of the story is that quantum mechanics is not a theory of just the small particles. It is a theory of nature. Okay? It applies to small objects, it applies to large objects, it applies to macroscopic phenomena. Superconductivity is not the only example. The fact that you are sitting in the chair and not falling through it requires an explanation, part of which involves quantum. Okay, just classical physics alone cannot account. Classical physics is an excellent approximation in many situations. It is not absurd. It's a great theory. But it is only an approximation. So the which-way experiment has been carried out. This is a very beautiful experiment carried out by Wolfgang Petterli, the Nobel laureate. Quite recently, this was published just a few months ago. With single atoms. So this is the direction in which technology is moving, and especially for the young scientists over here, they will be very interested in knowing about it. Now, quantum mechanics accounts for this which-way experiment, the quantum eraser, the delayed choice quantum eraser, in a very simple manner. Because what is happening is that the physical apparatus is no longer the same in every case. Okay? An apparatus in which the which-way experiment is not carried out, a Young's double slit experiment in which which-way detection is not attempted, is not the same apparatus as you have when you do a which-way experiment. Having done the which-way experiment, if you elaborate that apparatus further, in Hamilton's equations. The state of a classical system is described by position and momentum, the point in the phase space. Now, Einstein came up with many arguments because he thought that maybe there are some hidden variables which cause the origins of probability. So here is an experiment. You have a fission and two identical particles, shoot out in opposite directions. And you measure the position of the blue particle and measure the momentum of the red particle. And have you beaten Heisenberg's principle? Because using conservation principles, you can get the momentum of both and the position of both, right? So Einstein thought, in fact, the EPR paradox, as it is known, the Einstein-Podolsky-Rosen paradox, is somewhat more complicated than it. But the principle of the EPR paradox lies in similar arguments. And Einstein wrote this paper in 1935, and in the same year, this was in volume 47, and then in volume 48, Niels Bohr wrote another paper with the same title, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? That was the title because Einstein thought that the probability is coming from some incompleteness, from some hidden variables. And Bohr argued against Einstein's. So Bohr's intuition was correct, but his argument was not robust. Although his conclusion was correct, it was probably for, it just turned out to be correct, but not because the arguments were robust enough. And this debate continued for 30 years. And during these 30 years, quantum mechanics advanced, semiconductors came, lasers came, the whole technology, the computers came. So from 1930 to 1960. And John Bell's paper came in 1964. He wrote on the Einstein-Podolsky-Rosen paradox. And he came up with a method to resolve the Bohr-Einstein debate. Because Einstein's suspicion was that the probability enters the description of the laws of nature because there is something we do not know, and quantum mechanics is incomplete. So this was Einstein's goal. And John Bell came up with an argument to figure out whether such an argument will hold at all. And he came up with a mathematical inequality which you can actually test in an experiment. So let us talk about probabilities. You toss a coin, upwards or reverse, okay? And depending on what happens, you will win the toss. So why is there uncertainty in this? There is absolutely no uncertainty because if you know how much torque is applied, how much force is applied on the coin, okay? Can you see what I'm doing here? I have a coin and I am flipping it with my thumb. The top coin rolls up. I know exactly how much force I have applied, at what point I have applied. I can calculate the torque, I can calculate how it will spin and how it will land. Will it land on heads or tail? I can calculate exactly. It's completely deterministic. There's no uncertainty. But this works because we don't know where the force is applied. Is it close to the center or is it close to the edge? It is a hidden variable. We also don't know what is the moisture content in the air, so how it will affect the spinning coin. All these are local hidden variables. So Einstein thought that there must be some local hidden variables due to which uncertainties enter quantum theory. So you can test it. How do you do that? You look at not just one cricket match in which Dhoni is my favorite captain, but you have Smriti Mandana in another, and Rohit Sharma in another. Okay? And now you can look for correlations. Okay? Now keep track of this because I have got a red frame, a green frame, and a blue frame. I'm going to carry this color code in the next slide also. So keep track of that. I have RGB, red, green, and blue. And each color is double valued in two ways. Red may overlap with green or it may not. Also, red may overlap with blue or it may not. I hope you understand this significance. Overlap means both getting heads or both getting tails. Okay? So each color is double valued in two ways. Now let's take this forward. We are trying to understand if the uncertainty is coming from local hidden variables. That's what we are trying to do to resolve the Bohr-Einstein debate. So we have the red, green, and blue circles. They intersect. Okay, we have Dhoni, Rohit Sharma, and Smriti Mandana over here. Each section is double valued in two ways, just as we said in the previous slide. Red may overlap with green or it may not, and red may overlap with blue or it may not. Are we all together? Now let's play a game, something which I enjoy playing with my granddaughter. Okay, and perhaps you do it at your own homes as well. You have a cartoon over here, okay, stick it on the wall, and blindfolded, put your finger on the nose. Have you all played this game? Yes? Wonderful. Now ask this question. There are these three intersecting circles. Okay? What is the probability that you will touch one part or another? And measure this probability. Okay, we are playing a game in which there is a certain probability that you will put your finger on the forehead or on the left ear, or on the right ear, or on the chin, right? Now that question boils down to which segment of these intersecting three circles are you going to touch? So you have these 7 segments, okay? And you can do this exercise very easily. You will find that the probability of green not blue plus blue not red is greater than or equal to green not red. Do you understand the equation? The notation is quite simple, self-explaining. Anybody has any doubt? It's very easy to see. And you can actually work it out if you like. The probability of green not blue plus blue not red is greater than or equal to green not red. However, green not blue includes green not blue with red or without red. So that is the local hidden variable. And whenever you have local hidden variables, you have such inequalities. This is an example of Bell's inequality. And you can test it. Okay? Does this inequality hold or not? If it holds, it means that what you have not measured is measurable and it will feed into your earlier result. Okay? So that result can be easily obtained, and if you plug in the unknown which you had not measured with red or without red, then you get this equation and you can actually perform an experimental test. So this is called as counterfactual definiteness. Theories are referred to as counterfactual definite theory if a property has got a meaning whether or not you measure it. Okay, the yes red or not red is a property which can be talked about if you don't measure it. The two inequalities are essentially the same, and it is like asking, is the moon there if nobody is looking at it? And this is not my question, this is exactly the question that Einstein asked. He asked this question, is the moon there if nobody is looking at it? But there was a very nice article in Physics Today 2 decades ago with this caption, is the moon there if nobody is looking at it? Now, these inequalities can be tested. And this is the work of John Bell, that he came up with a very simple mathematical statement. You have two sides of an equation, and they are either equal or not equal, or greater than or less than. So there is an inequality over there. And it turns out that Bell inequality must be satisfied by all theories which are both local and counterfactual, because the hidden variables over here are all local. Which means that you have to sacrifice either locality, which means that the difference between here and there disappears. If locality is destroyed, our sense of reality is challenged. Okay, because we have a certain sense of the particle being inside the apparatus or outside the apparatus. Okay, we talked about the particle, the lens being kept outside the apparatus. But there is nothing like inside and outside. Because you must sacrifice your sense of locality to interpret reality. I like to call it as reality 2.0, which is different from our orthodox view of it. So quantum theory is either non-counterfactual or non-local. So this is the meaning of the non-local reality in the universe. And this is celebrated as the most profound discovery of science, because just imagine, means two intellectual giants like Bohr and Einstein debating with each other. Nobody is able to resolve that debate. Neither Bohr and Einstein themselves, nor anybody else who was there at the Solvay conference. The debate started in 1927. It continued into their papers in 1930s and 1935. His papers went on for the next 3 decades. And this could be resolved by John Bell's work. Incredibly important work. So you have seen this Feynman's path integral approach, which I showed you earlier, that all of these different paths, which go right up to the Mars or Andromeda or something, all of them will add up. They become powerful tools in quantum computing, because classical computing is determined by Boolean algebra, and as I mentioned, I was introduced to Boolean algebra when I was failing miserably in my undergraduate exams, and Professor was struggling to take me to that mathematics professor in Randaspet, which is where I picked up some symbolic logic. You must add up all of these histories, all of these alternate paths. Okay, the superposition of all of these paths is what must be taken into account. And I'm going to read out something from Philip Shore's paper. This is straight out of Philip Shore's 1994 paper. Everybody has heard about Shore's algorithm, right? What does Shore say in this paper? In quantum physics, an experiment behaves as if it proceeds down all possible paths simultaneously. A quantum computer behaves in much the same way. The computation proceeds down all possible paths at once, and each path has associated with it a complex amplitude. These are the amplitudes which you must add up. This is the sum over histories. To determine the probability of any final state of the machine, we add the amplitudes of all the paths which reach the final state, and then square the absolute value of this sum. These words you could have seen in the earlier figure in which I talked about Feynman's path integral operation. Exactly the same language, exactly the same principle of superposition, and it is used verbatim in Philip Shore's paper. What happened? My talk is over or what? I'm not done. May I have some water?
Yeah, it is there in the table. It is there.
Maybe he figured out that I need some water. Nagpur is quite warm coming from Bangalore. Bangalore is so pleasant. Lovely weather all around the year. Let's go down all the slides. Go down quickly. Yeah, go down further. Yeah. But good that flashback showed you the multiple paths which you are seeing in Philip Shore's paper. Next. Yes, we were here. Yeah, go to the next. Yeah. Can I use my remote now? Yes. So this is almost something from Hogwarts, right? This is magical. But that is exactly how nature functions. And our job as scientists and engineers is to interpret this. And I think Sudha is telling Kamaldi that I've learned about Hogwarts from our granddaughter. Okay, here we are. And now the power of using a superposition of 0 and 1. Because all the classical computing is done using classical gates. The AND gate, the exclusive OR gate, NAND gate, all of this is done using binary logic, Boolean logic, 0 or 1. And now we are talking about the superposition of split 1 and split 2, superposition of yes and no, superposition of dead and alive. Not just the cat, but even you and me. Everywhere you have this superposition. And you can explore the alternative possibilities which are mutually excluded from each other in classical physics. But nature demands that you must include them, but not using classical logic, but using quantum logic. You must use the quantum principle of superposition, talk about probability amplitudes, their coefficients, their modulus square, and use probabilistic laws to interpret your results. So that makes quantum physics very powerful. Like you want to go to the airport from the VNIT, there are many ways, many different roads that you can take. You can take a left or a right and then find a roadblock and then recover from it. But if you can explore alternatives simultaneously, you will end up arriving at your result much smarter. And this is what you need if you want to come up with a new drug to treat cancer. What would you do? What do research labs do? They try different molecules. They don't know what ligand will work. And they carry out hundreds of experiments for which they need thousands of young scientists in tens of different laboratories. And it becomes a very expensive thing. But if you can explore these different mutually exclusive alternatives in one calculation and arrive at probability, you can get your answers much more efficiently And that is where quantum computing becomes so powerful, because you can use the superposition of 0 and 1. And let me illustrate this power through this particular example that I've chosen. Let's do a 6-qubit quantum computation. And there are 6 qubits which can be in either state 0 or 1. A general state would be a superposition of 0 and 1. And you can ask a question that if you have got a given superposition, and this is a given superposition, this is a superposition of 4 terms. You can quickly check that it is normalized. The sum of the squares will add up to 1 if you take the coefficients. And you're asking the question that, okay, you start with this superposition, and in how many steps can you get a superposition in which you have got these 7 terms? Now, how will you do this problem? You will flip a 0 to 1, 1 to 0, then do something else in the next step, and then do something else in the 3rd step, and then something else in the 4th step. You will need thousands of steps to get this right answer. Don't try. You will need thousands of steps. But if you do it with a superposition of 0 and 1, because it is exploring slit 1 and slit 2 simultaneously. So this is parallel computing in a very different sense. It is not like giving part of a problem to one processor and another problem to another processor, and then combine the results as long as these two are independent of each other. Okay, so that is classical parallel processing. Here you're exploring the parallel alternative paths at once, because that is how nature is. So if you use this parallel computing, which is what nature provides, and one of the earliest codes in which this was done was a code by David Deutsch, in which he explored such a problem, but I will not get into that. Maybe some other time I could talk about it. But if you use this power of quantum computing, you cannot use the classical gates, of course. You need quantum gates because they are manipulating the superposition of 0 and 1. And using quantum gates in one step, you can get this. In the second step, you get this. And then in the third step, you get the answer. Huh? So this is the power of quantum computing. Okay. Otherwise, if you were to keep flipping 0 to 1 and 1 to 0, and then end up with this, you would need thousands of steps. I will talk about technology now. From Enigmas to technology. And the technology that is of particular interest to me is our own security. 80 to 90,000 square kilometers of Jammu Kashmir are occupied by Pakistan, 44,000 square kilometers by China. And the memories of all these terrorist attacks are fresh in our minds. Now, these issues have to do with our survival, with our existence. As humans, as societies, as a nation, we have a very nice set of missiles which have got different range around our country, up to different ranges. But mind you, if you fire a bullet and the target is 1 kilometer away, just 1 kilometer, maybe the VNIT gate, right? And you fire a bullet, by the time the bullet reaches the target, the earth has rotated. And the target is no longer where it was when you aim for it. So you have to make a correction for it. In fact, the bullet would miss by as much as 8 inches above the bullseye or a few inches below the bullseye at a distance of just 1 kilometer. You have to make these corrections. If you fire from the North Pole and your target is at the equator, and if it is a missile, then the Earth would have rotated to 15 degrees. And how much is that in kilometers on the Earth's equator? Can you do a simple calculation in your mind? It's about 1600 kilometers. You'll be nowhere close to the target. Okay, you can't. Alright, so all of these corrections have to be done. And the bullets and the missiles have to be directed appropriately so that they hit the target. So missile navigation is a very advanced technology. So this can be done using accelerometers and so on. So there are various technologies available for that. But these days one uses satellite-based navigation. We have our own navigation system developed by ISRO. And it consists of these 7 satellites. And how are the missiles navigation carried out? You need precise calculation. Time is an essential factor which must be controlled, right? Which must be measured very accurately. Otherwise, you cannot control the missiles. You need very precise clocks for the physics. You need atomic clocks. You need very accurate atomic clocks. You know the Bohr model. The Bohr model of the hydrogen atom is on the left, but then it is more complicated than that because you have relativistic corrections and so on. You've got the spin-orbit splitting, and then you also have the hyperfine structure. And if you look at the transitions, these are actually non-dipole transitions in the hyperfine structure of the hydrogen atom. In fact, this is what is used to study the cosmos, hydrogen 21 centimeter line. And the atomic clocks actually don't use hydrogen atom, they use the cesium atom. So the cesium clock is what sets the standard. But you can also have secondary clocks which are made of rubidium, and one uses the rubidium quantum atomic clock for this navigation. So this technology is essentially driven by quantum laws, but not just the quantum laws, also the theory of relativity. Not just the special theory of relativity, but also the general theory of relativity. How? If you have twins, one is a homebound twin and the other is traveling in a rocket, the traveling twin ages less. Okay, this is the twin paradox. It was created by Albert Einstein himself to account for time dilation and length contraction. Where does it come from? It comes from Maxwell's equations. Because from Maxwell's equations, if you take the curl of the curl equations, there are 2 curl equations and 2 divergence equations. If you take the curl of the curl, you get the wave equation. What does the equation tell you? That the waves travel at the speed of light, 1 over mu 0, square root of mu 0, epsilon 0. So the speed of light is determined by properties of vacuum, nothing. Is that not absurd? Because when you talk about the speed of anything, you rock. And I measure your speed, but if I chase you, your speed is something else. Right? And here, the speed is not determined by the observer, but by nothing. Why so? This is strange. This is absolutely counterintuitive, mind-boggling, and it needs the mind of Albert Einstein to figure out that if speed is constant, what is speed? Distance over time? Distance must change and time must change. So he concluded that there has to be time dilation and length contraction, and that accounts for the fact that the speed of light is constant. But the time for a moving clock will not be the same as the time on a stationary clock. And the atomic clock, which is on the satellite, it is moving at something like 11,000 kilometers per hour. So it has got tremendous speed. It does not click at the same rate as a clock on Earth, with which it has to synchronize. So that has to be calibrated. But then there is something else. Your head ages faster than your feet. A taller person ages faster than a shorter person. So then, sorry. So that was one of the tallest persons in our research group. And that is because of the gravitational redshift. Okay, there is a gravitational shift and aging process. And you can actually measure it. You can measure it very accurately. So the time, the clock, atomic clock, the hyperfine structure clock on the satellite is clicking differently than a clock, atomic clock on the ground, with which it has to be synchronized. Synchronized in the sense calibrate. Okay? So there is a time dilation as a result of the fact that this clock on the satellite is moving at 11,000 kilometers per hour. It clicks at about 7 microseconds slower per day, and that is an important correction which must be taken into account. And because of the gravitational redshift, here is a picture of an optical lattice clock, and you keep it here and measure the time interval, and you raise this clock through 2 centimeters, but it is now in a different gravitational field. The gravitational potential is different. You raise it through just 2 centimeters, and you can actually see the gravitational time dilation. This optical clock measured it in 2017, but then in 2022, this clock measured it at a millimeter scale, not just a centimeter. You raise it just to a millimeter, and you could touch it. So the young scientists over here are working with this accuracy of technology. Both theory and experiment is very challenging. Actually, there are new experiments. Just a few months ago, middle of last year, May 2025, an atomic clock ensemble has been installed in space at the International Space Station, ISS, where they expect to be able to improve this accuracy to sub-millimeter. Awesome, is it not? So the satellite is at 36,000 kilometers higher up, which requires a correction of 45 microseconds quicker per day. And if these corrections are not made, the navigation of missiles will not work, your cell phones will not work, your internet will not work. And all of this is very advanced technology which relies on quantum physics and also on the theory of relativity. BrahMos is one of the most accurate missiles. It can find its target within 40-50 centimeters. There is no other missile system in the world which is as accurate as it. And this makes you, it is called BrahMos because it is the word comes from Brahmaputra and Moskva River in Russia. It is a collaboration between Bharat and Russia. So we also use the Russian navigation system. We use the GPS, and we also use our own navigation to monitor BrahMos movements and our missiles. And now I come to another part of technology, which is information processing. And Alice wants to convey some message to Bob. Okay. And sure enough, somebody will try to intercept it. It's not always this bandit, it could be your parent. And how do you encrypt the information so that it is not intercepted? Now, this is the fundamental question. And it is of importance in everything, not just in your emails crisscrossing the internet, your WhatsApp messages, pictures. But there are many more important things like defense related material. Information has to be secure. And this is now done using encryption techniques which were devised by Revesh, Shamir and Alman. So this is called the RSA encryption technique, which some of you must be familiar with. This was developed in the 1980s, and it is based on very simple logic, because you all know how the exclusive OR gate works. Okay, so here is a simple truth table for the exclusive OR gate, and you know that if z is equal to 1, x must be the opposite of 1. So if you don't know y, you can find out what y must be from z. So you can use this logic, and suppose you have to send information about 3 bytes of 8 bits each. What will you do? You have got 24 bits, and you have them set up over here. This is the information Alice wants to send. And Bob has got a key which he has developed along with Alice in advance. And because of this key, using the XOR gate, from the Z, he can find out what X must be. Okay? So this can be done. Now, what if that code gets, leaked? And that is the reason the RSA algorithm came up. It is based on two keys. So a private key and a public key. And it is driven by the mathematics of factoring numbers. If you have got two numbers, you can multiply them very easily. But if you are given a bigger number, then it is very hard to find its factors. So this RSA algorithm is based, it makes use of Euler's quotient function and so on. I will not get into the mathematics, it's not very difficult. But the question that is posed, and this was in 1991, I think, these numbers were generated on machines. These machines were not connected to any network. Their hard disk was destroyed so that it is completely secure. And these numbers have been used in all the encryption that we are using in the world today, whether it is in banking sector, defense sector, email sector, network, or everything. Everything is governed by these RSA algorithms. Here is an example. RSA 768, this is a number which has got 232 decimal digits, and these are the factors. How were these factors determined? So this was factored in 2009, so this was a little more than 15 years ago. Well, this is recent, okay, this is actually happening. And these were factored on December 12, 2009. The CPU time spent on finding these factors by a collection of parallel computers amounted approximately to the equivalent of almost 2000 years of computing on a single core 2.2 gigahertz machine. But that is what makes cracking this so difficult. And the RSA encryption works because of this difficulty. However, the biggest problem is RSA 2048, which is not the 617 decimal digits. And now with the Shor's algorithm, because now it is not exploring slit 1 and slit 2 separately. Okay, you saw Shor's paper. And he told you that, okay, even if there are millions of paths in Feynman's double slit experiment, all of these can be processed simultaneously. So Shor's algorithm has the capacity to crack the RSA encryption very quickly. It has not happened as yet, but Davos, it became so famous because Trump claimed Greenland at Davos. But it should be more famous for this because it was also reported by the IonQ chief executive officer at the same meeting in Davos at the World Economic Forum that the RSA 2048 is likely to be cracked in the next 3 years. So it's happening. It's happening anytime now. So it's a very serious thing, which is why quantum computing is essential. This is my last slide, which is a tribute to Deutsch, Shor, and Love Kumar Grover. Love Kumar Grover is, of course, a hero, a student like one of you who grew up at a small town in Uttar Pradesh in Meerut. You know where Meerut is? So he grew up at Meerut. And in the days when there was no internet, there was no Google, there was no Copilot, no ChatGPT. He, after finishing his BTech from IIT Delhi, very soon, in just another 15 years, where was he reading the papers? Now we read it on the internet. So within 15 years, he proposed what is famously known as the Grover's algorithms. Great hero for all of us. Thank you very much. I will be happy to take questions. Sorry, I spilled water, but Sudha usually says that I spill the beans. Questions? I must thank everybody over here. I must tell you how much happy I am to see Uday and Ram Karthik over here. I'm meeting them after a long time, and it's absolutely a great joy to meet both of you. We were very proud of them when they were students at IIT Madras. Now we are even more proud for what they are doing here.
So one question is, very much thankful to the very live explanation of quantum to our students. And question is, where do you see this technology in next 10 years or 15 years? Technology-wise.
I can't even see where it will be tomorrow.
Oh, great.
It is changing so fast that even those who know about this field much more than me cannot really predict where it will be tomorrow, let alone 10 years from now. Life will be very different. And life is very different today than what, Mukund and all of us for PhD students. No, the kind of technology we are using today is very different from what it was a few decades ago when we were students. We had never imagined this. So we are in for many changes. The important thing is to stay up with the technology. Every day you must learn, and learning has become very easy because of AI tools. So what used to take me a lot of effort and many hours to go through books and journal papers and so on, I can learn much quicker by prompting an AI tool. So I strongly recommend that all our students learn very rapidly, stay up with the technology. 10 years from now, I can assure you that classical computers will not be replaced by quantum. They will continue to be used. But how they will be used will be different. Okay? Because there will be certain driving tools. There will be some engines. So I think it is extremely important to stay up with the technology. And the key lies in accepting one very simple thing. आपके पिता कौन है और उनके पिता कौन है? उन्होंने गणित किया, आप भी कीजिए. Okay? The key lies in mathematics. And please embrace mathematics. If you don't do it, you will be outsmarted very quickly. And it's very simple mathematics. Just think about linear algebra. Solving simultaneous equations. What's the big deal? High school kids can do it. Right? Now, there is a mental block which many teachers face, and then they transmit it to their students. And then it gets multiplied by a factor of 100, which is a disaster. And I think in the last 20-30 years, we have done a lot of damage already. So it's very important that we take some corrective measures, plunge into it, take it head on. It's very simple. Because the Bichway experiment, the quantum eraser, and then the delayed choice quantum eraser, which I talked about, can be so easily explained by the orthogonality of the states M1 and M2. You just have a different Hilbert space. It's very simple. There is no other way you can explain it. Quantum mechanics has not failed you for over 100 years. People have asked, is there another theory to which quantum physics is an approximation, just the way classical physics is an approximation to quantum physics? People have asked this question, but I'm aware of some literature on this. I can share those papers with you. But the best answer is that there is an existence theorem which tells you that such is not the case. So there are existence theorems, no-go theorems, and so on. I won't go into those details, but that's very interesting. So I don't think there is any theory which is likely to supersede quantum physics. Very unlikely. Not impossible, but very unlikely. So it is best to learn it. And learning it is very easy. So my main objective in meeting faculty and students today was to convince you that embrace linear algebra. Okay, begin with that, and the rest of quantum physics is very simple. Very rarely do you have to go beyond the second order differential equation. High school students know what the limit of a function is, what is the derivative, what is the second derivative, what is the big deal? All you have to do is to apply boundary conditions, solve.
Pardon me for one more question.
Sure.
People are also talking about consciousness and quantum. is there any real something happening, or it is just a imagination?
Good question. And I can't say that I had not expected it, because many people there's a lot of material on the YouTube, and when you talk about this non-local reality, the difference between here and there vanishing and so on, and they immediately jump to connect it to Jagan Mithya. That is an absurd conclusion. Okay, quantum entanglement and what I call as reality 2.0 is between entangled qubits. It's not between arbitrary two objects. If you begin to say that, okay, everything is connected, and quantum physics has given a proof for that, it is total nonsense. That's all. It has absolutely nothing to do that. It is not supernatural. It is not spiritual. It is very physical. It is as physical as the chair and the microphone and every object that you're looking at. Okay? It is as physical as that. There is nothing supernatural about it. There is nothing spiritual about it. It's completely physical. The entanglement is a physical entanglement between qubits. It is not a spiritual entanglement. Have I answered it? Yes. Right. Yeah. It may not be a very popular answer. No. Sir. So I'm very. Let me just take half a minute to complete this. I'm very proud of the philosophy behind this. Okay. In my own very humble way, I do read it, I do study it. I'm very proud of it. But it is absurd to carry it beyond its limits. I think it is important to be proud of our heritage for the right reasons. Okay, that is the reason I refer to Bhaskaracharya, Aryabhatta, Pingala, which I always do. Okay, the Fibonacci sequence is not Fibonacci's. Before that, it was Varahamihir. Before Varahamihir, it was Pingala. So we should be very proud of our heritage. And I'm going to talk about it on Monday about this. But if we connect it with the wrong things, we discredit the achievements for which we should be legitimately proud. So we should celebrate that and not jump to this Jagan Mithya or reality, failure of reality is the same thing. No, it's completely different. Sorry, I'll take your question.
Yeah. So some small questions. So now government it is focusing on this quantum mission and other things, right? So whatever the newcomers are coming up, whether they have to train in the theory part or software or maybe technology experimentation, so that they can be ready for the new technologies.
Yeah, good question. Quantum technology is not just quantum physics. Okay, quantum computers is not just physics. You need cold atoms, for example. How do you make cold atoms? How do you do refrigeration? How do you reach those temperatures? You need mechanical engineers, you need electrical engineers, you need civil engineers. Okay, the laboratories have to be built such that they will be vibration proof. To carry out those experiments, you need civil engineering. So quantum technology is an integration of many disciplines. You need mathematics, you need physics, you need engineering, and you need all branches of it. What should students do? I think they should focus on identifying their aptitudes. Okay. यदि आपको हॉकी खेलना नहीं जमता तो मत खेलिए ना, कुछ और खेल लो. So if you can do mathematics and vector algebra, do quantum physics. If you're good at, you know, soldering and so on, get into electrical engineering. So I think there is no single answer. For every individual, it will be different, and he or she must find out what works best for the student. And have faith that if you're good in anything, you don't need it for quantum. Because quantum technology requires every talent, absolutely every talent. Either look at those neutrino detection experiments which were being attempted, and you have to dig. You need geologists. Whatever you're doing, do it well, do it with pride, and don't go by any hype. Like I told you, I never wanted to become a physicist. I wanted to join the armed forces. But finally, when I got into physics, I've enjoyed it. And I've done physics because I enjoyed it. Do what you enjoy. Do what you love. Do it passionately. Then you can contribute something. Then you don't have to worry about jobs. Because if you're good at something, you will get a job. So I don't. Yes, please.
Thank you very much for such a wonderful talk. This reminds me of the Professor Balakrishna's talk. Actually, I attended at IIT Madras. I think, of course, I was decade back. The question is because you mentioned that quantum mechanics and then the classical mechanics theories, and then I think in line to that, what other theories actually can be from that kind of most generalized one. I think this string theory is one of the most interesting ones what people have talked about in the last 30 years. And I think this is the time when string theory is going through one of the most serious criticisms, I think, according to recent discussions actually. I think that is uploaded by IAI actually YouTube channel where Professor Penrose and Professor Brian Green and Professor Eric Weinstein actually they discuss and then try to rule out the string theory completely. In line to that, how you feel that, what is your comment that to deal with the way forward, to deal with the mathematical inconsistency what gravity brings into quantum mechanics?
Yeah, I know. Very good question. I certainly don't have an answer for it. I have no apology for it because I don't think anybody has an answer for it. Absolutely nobody. Most experts don't mean they are interested in Penrose's theory, but not everybody is in agreement with that. It remains speculative. It has the potential of being a fundamental explanation of the universe, but not necessarily so. And I don't think that physicists at large find agreement with each other and with Penrose on this. That is the best answer.
Thank you.